Hello everyone, we are in the lecture number 11 of chemical equilibrium, a thermodynamic approach. Here we are going to discuss influence of introduction of inert gas on equilibrium constant. Here inert gas means the gas or the substance which does not take part in the said reaction. Suppose the reaction is taking place between two substances A and B, and number of moles of A is small letter a and number of moles of B is small letter b, producing Cc and Dd. Okay, here some substance E, suppose say E is taken, which does not react with any one of them, A, B, C or D. Okay, so in that case this is an inert gas. It is not necessary that they have to be helium, neon, argon, krypton, xenon, radon. It may be some other gas also which is not taking part in this said reaction. Okay, so the value of equilibrium constant in terms of pressure is Kp, and the relationship of Kp with Kx is Kx into P to the power delta nu, and the expression of Kx, if written here, that means mole fraction of C to the power C, mole fraction of D to the power D divided by mole fraction of A to the power A into mole fraction of B to the power B, then it gets the form like this form into P to the power delta nu. So Kp may also be written as xc to the power C, xd to the power D divided by xa to the power A, xb to the power B into P to the power delta nu. Okay, now we know that if temperature is kept constant, then Kp is definitely constant. Kp only changes with respect to temperature. Okay, and with no other parameter. It is only temperature dependent. So if temperature is kept constant, the value of Kp is constant. And if now the parameter, the fourth parameter, that means some introduction of inert gas is changed, okay, that means some inert gas is introduced, then the system would try to keep the value of Kp constant so that it is not disturbed according to the Law-Chatelier principle. Now if some inert gas be introduced into the system at constant temperature and pressure, then the right hand terms in the above equation would adjust themselves so as to keep Kp constant, as I have said here. Okay, now if Na, Nb, Nc and Nd are the number of moles of what? Now A, B, C and D respectively. Okay, these are their number of moles, respective number of moles. Okay, that means you are taking this number of moles. This is not small letter a, this is not small letter b. This is the number of moles you have taken. Okay, arbitrarily taken by the taken in the experiment. Okay, this is not the stoichiometry of A. Okay, so do not get confused with small letter a and Na. Na is not the stoichiometry of A. It is the number of moles of A here. Okay, sometimes small letter e is called number of moles of A, but this is the stoichiometry. But here this is purely number of moles of A which you have taken. Okay, and this is not the stoichiometry of A. Okay, if 0 moles of an inert gas is introduced into the system, then there would be a total Na plus Nb plus Nc plus Nd plus N0. This amount is now introduced into the system. There had been total, what was the total number of moles in the system? Na plus Nb plus Nc plus Nd. But now, after having introduced the inert gas, the total number of moles in the system is the overall previous number of moles plus N0, and this is denoted as summation of N. Okay, this amount is now present in the system. So sum over N number of moles of the system is now present here. Okay, in that case the mole fraction would definitely decrease for all the systems. This one had been Na divided by the summation of this 4. Now Na divided by summation of the 5, isn't it? So the corresponding number of moles has been changed. Xa becomes Na by summation N, Xb becomes Nb by summation N, and so on. Okay, up to Xd. And if these values are put in the expression of Kp, what we have just derived, then we can write them in this form. Okay, Nc by summation of N to the power C, Nd of summation of N to the power D. Okay, divided by Na of summation of N to the power A and Na Nb divided by summation of n to the power b. Okay, now this 1 by summation of n part is taken out of this fraction of this rational part, then we can separately write it as 1 by summation n to the power delta nu, because delta nu is nothing but c plus d minus a minus b. Okay, and here in the power of p also there is delta nu, so we can merge them and write p by summation of n whole to the power delta nu. Okay, and here this nc to the power c, nd to the power d, as usual they are repeated here, and here na to the power a and nb to the power b, they are also repeated here the same way, na to the power a, nb to the power b, and this is our equation number 1. Now let us consider 4 cases here. Okay, out of this, the first 3 cases would be taking place at constant pressure, and the 4th case would be taking place at constant volume. So the cases at constant pressure, there will be 3 cases. Okay, now let us discuss case 1. If total pressure is constant, okay, and delta nu is 0, that means the number of the stoichiometry of products and stoichiometry of the reactants, if they are same, in that case delta nu equal to 0, then let us put delta nu equals to 0 in equation number 1. Okay, so we have put delta nu equals to 0 in equation number 1, and this part within the bracket becomes 1. Definitely something to the power 0 must be equal to 1, and in that case Kp has the expression nc to the power c, nd to the power d, na to the power a, b into nb to the power b. So there is no change in the value of Kp. Kp is same. Okay, Kp remains undisturbed here because we are getting this equation here. Okay, now case 2, if for total pressure constant, definitely P is constant here, but delta nu is positive. Okay, in that case this value, okay, this value would decrease if this delta summation n is increased, isn't it? Because P is constant, so this has some extended value. Okay, then delta nu is positive, so this value must decrease. So if this value decreases, in order to keep Kp constant, this one must have to increase. Okay, this one means the numerator would increase and the denominator would decrease. That means the reaction would shift to the right hand side, that means to the forward direction. So in that case, if delta nu is positive, in that case P by summation n to the power delta nu decreases with increase in delta n. Why summation n? Why it increases with this value increases? The answer is, since some inert gas is introduced in the system, then this value would increase, because this value has a summation of 5 moles, 5 number of moles of 5 number of substances, isn't it? So it is Na plus Nb plus Nc plus Nd plus N0. So N0 is increasing, so this one would also increase. If this one denominator increases, then it has some power, positive power, then the overall thing decreases. If this one decreases, then in order to keep Kp constant, this one would have to increase. That means the numerator would have to increase, that means the denominator would have to decrease, that means the reaction would shift to the right hand side. Okay, so this is case 2. Now case 3. In case 3, at constant pressure, if delta nu is negative, so with increase in the value of summation n, this value would definitely increase, isn't it? Because this is negative power now. So if it has some negative power and the denominator increases, then the overall value would increase. If this one increases, then in order to keep Kp constant, this one would have to decrease. So if this one wants to decrease, then the number of reactants would be increasing and the products would be decreasing. That means the reaction would shift to the backward direction. So if delta nu is negative, in that case P by summation n whole to the power delta nu increases with increase in summation n. That means if some inert gas is introduced in the system. Therefore, in order to keep Kp constant, the first term of the right hand side of the equation 1 would decrease, that is, the reaction would shift towards right. And finally, the fourth case, where pressure is not constant, the volume is constant. Okay, That means the container is not changing. In the same container, the whole thing is happening. So try to imagine, try to think over this. What should happen? If there is a closed jar, within this the reaction is taking place, and within the same jar you are introducing some inert gas, should there change in the in the value of Kp? I think the answer should be no, because the volume remains unchanged. That means the partial pressures also remaining unchanged. Okay, so we have to start from this way. Pv equals to nRT, V and T are constant. We have kept volume constant, and temperature is constant. Previously we have mentioned this. Okay, so we have now two variables, P and N. So they would follow the relationship P versus N, and definitely N is also equivalent to summation N. Okay, then if this one proportional to this one, then their ratio should be what? The ratio should be constant. Okay, then therefore this is a constant ratio. Then whatever be the value of delta nu, it does not affect the value of Kp, because here on increase or decrease, whatever it is done, the pressure would also change itself. If inert gas is introduced, then pressure would also increase, then the ratio is same, isn't it? If inert gas is introduced something more, then pressure would increase something more. Okay, then the ratio is again the same. Then whatever be the value of delta nu, it does not affect this ratio. Okay, if this part is not affected, then this part is not also affected, then the numerator denominator also not affected. That means Kp remains undisturbed. Okay, so these are the four cases discussed. Thank you. Have a nice day.